So today we take a look at the history of the Earth and how it's divided into various different periods. Starting with the fossil record and geologic timescale. It's estimated that the Earth formed along with the solar system about 4.6 billion years ago, which is 4,600 million years ago. The geologic timescale is a summary of the major events in Earth's history. It's broken down into 4 time segments. The first one is the eon, which is the largest segment of geologic time. The next one's the era. Eras are broken down into periods, and periods are broken down into epochs. Epochs being the smallest segment of geologic time. One thing it's important to understand is the difference between relative time and absolute time. Relative time places events in a sequence, but does not identify their actual date. So it's like a chronological timeline with no actual dates. It just puts things in the order in which they occurred. Actual time gives you, of course, the actual dates of geologic events. So, for example, relative time would be a list in chronological order of what you've done today up to this time. So maybe you woke up, and then you brushed your teeth, and then you ate breakfast, and then you put on your clothes for school, and then you got in a car or on the bus and came to school. Whereas absolute time would tell me that you got up at 6:50 and then you brushed your teeth at 6:52 and you ate breakfast at 7:03 and so on and so forth. So if we look at relative time, we can use that to find the age of rocks. There's something called the law of superposition, which means in undisturbed sedimentary rocks, the oldest rock layers are at the bottom and the youngest are at the top. So sedimentary rocks, remember, form when dead organic material piles up, and then under pressure and time, those minerals and other things become rock. This would just say that the bottommost layer, as long as there hasn't been any geologic event to disturb it, like an earthquake or a volcano or tectonic plate shifting, the oldest layer would be at the bottom. So if you look at our picture here, we've got layers A through I. That means the oldest layer would be A, and the youngest layer of rock would be I. Specific environmental conditions are necessary in order for fossils to form, and there are many different kinds of fossils. Fossils can form in several ways. First way is called permineralization. This occurs when minerals are carried by water, and then those minerals get deposited around some sort of hard structure like bone. So the organism has died, the living tissue or the dead tissue, organic matter, has already been decomposed and eaten away by other organisms. So all that's left here is the skeleton. Water carries and deposits minerals that surround this and then forms a fossil. Another way is called a cast. A cast forms when flowing water removes all the original tissue and leaves an impression. Trace fossils specifically record the activity of an organism. So footprints are called trace fossils because they show what the organism was doing. They show perhaps where the organism was going and how fast it was going, things like that. Another type of fossil is something preserved in amber. This is a tree resin that has hardened after the tree's been buried, and an organism happened to be caught in that resin at the time. You also have something called preserved remains. These are formed when an entire organism becomes encased in a material such as ice. This is obviously different from amber because amber specifically refers to tree resin or sap. It's important to remember that you have to have specific conditions for fossilization. So very, very few things actually become fossils. The organism has to be intact. It has to have not been carried away by predators or by things that decompose the material. The skeleton has to remain intact in order for it to become a fossil. And then whatever weathering patterns are going on in that location at the time, they have to allow for fossilization to occur. So sometimes that just doesn't happen. One way to know how old a fossil is through relative dating. Relative dating estimates the time during which an organism lived, which compares the placement of those fossils in the layers of rock that they're found in. Scientists then infer the order in which the species existed. So if you see layers of rock like this, which are very common in Pennsylvania actually, the fossils that might be found in rocks like this can be dated based on what we know about the rocks that surround it. Another way to provide the age of fossils through radiometric dating. This is a much more accurate way. Radiometric dating uses the decay of unstable isotopes. We learned earlier this year that an isotope is an atom of an element that has a different number of neutrons in its nucleus. So most commonly we use carbon-14, which is an isotope of carbon, to do radiometric dating. Carbon-14 has 8 neutrons, whereas carbon-12, the most common found isotope of carbon, only has 6 neutrons. What we look at when doing radiometric dating is the half-life. The half-life is the amount of time it takes for half of the isotope to decay. So if you know the percentage of carbon-14 in the particular specimen that you have or the fossil that you have, you can figure out how old it might be, because we also know how long it takes for half of the carbon-14 that exists to decay into something else. So the geologic timescale divides Earth's history based on major past events. So it might be a mass extinction event, it might be an ice age, it might be a major climate change. And so we divide Earth's history based on these particular events because they give us a good, easy way to recognize, okay, something major changed, and that changed all of the flora and fauna in a particular area. Index fossils are also used to determine the age of rock layers. Index fossils are things, living organisms that existed only during specific spans of time, and they are widely spread out. So things like trilobites are often found, fossils of these are found everywhere. And so we know they only existed for a particular period of time, so we can use that to figure out the relative age of a layer of rock. So the history of Earth is represented in what we call the geologic time scale. The majority of Earth's history is in pre-Cambrian time. This includes the oldest known rocks and fossils, the origin of eukaryotes, and the oldest animal fossils. Eras, which we know are a period of time, last tens to hundreds of millions of years. So eras last a really long time. They consist of at least 2 periods. We have 3 major eras in Earth's history: the Cenozoic era, the Mesozoic era, and the Paleozoic era. And they are characterized with particular periods. The Cenozoic era is the most recent. It contains the Quaternary period, or the Neogene, and the Tertiary period, or the Paleogene. And you can see some of the organisms that include or that exist in the Cenozoic era. Then we have the Mesozoic era, which contains the Triassic period, the Jurassic period, and the Cretaceous period. This is when the dinosaurs roamed the earth. And then finally we have the Paleozoic period, or era, which contained the Permian period, Carboniferous period, Devonian period, Silurian period, Ordovician period, and Cambrian period. And here you can see some of the types of organisms that existed in each period. And The MYA here means million years ago. So based on what you know, try and figure out what era and period humans now exist in. Periods last tens of millions of years. They're most commonly used units of time on the time scale, and they are associated with rock systems. For example, the two periods that are most recent, the Quaternary period and the Tertiary period. Mesozoic era, again, contains 3 periods, and the Paleozoic era contains 6 periods. Epochs last several million years, so these are the smallest time segments.